proceed.
Thank you. Thank you. Well, it's a great pleasure to give this talk, and thanks for the invitation. And so today I'm going to talk about higher order fluctuations in dense random graph models. We've just put the preprint on archive a few days ago. This is joint work with Gursharn Kaur, who's currently my postdoc in Singapore. So let me give a quick overview over the talk. I want to first talk a little bit about what dense graph limit theory is, just a very short introduction, give you sort of the problem statement, what we're interested in, then sort of an executive summary of our results, so that so they get sort of the higher level view of these results. Then I go and maybe a little bit into more detail and talk a little bit more about the specific approximation theorem that we're using, and then followed by some discussion about this particularly statistical applications of the results. And if I have time, I will go into the more details of the orthogonal decomposition that is underlying this sort of approximation result. Although I doubt I will have time, but let's see how it goes. So all right, dense graph limit theory was sort of initiated by Lovas and Segedi in 2006. And what do we mean by a dense graph sequence? That's essentially a sequence of graphs here where the number of edges in the graph scale like the number of vertices squared. So these are dense in the sense there are a lot of edges. And while these graphs are not realistic, because most real networks tend to be not that dense, so the practical applications are limited, but it's sort of mathematically the theory is the most elegant in this dense regime, and so that's sort of the good starting point to see how what sort of to develop a theory that I will talk about later. And of course, we can, without lots of much generality, we just assume that Gn has n vertices just to make life easy. Now, one way to analyze these dense graph sequences is through their subgraph, so-called subgraph densities. There are other ways to analyze them, and they're sort of in this dense world, they are equivalent, but the one we're interested in for this talk are the subgraph densities. So let's assume we have a dense graph sequence, and we fix a finite simple graph on k vertices. I should say that all graphs we consider here are finite, simple, that means no loops and no multiple edges, and undirected as well. So let's have a finite graph on k vertices fixed, and so we define the subgraph density of f in Gn to be denoted by the symbol T sub f of Gn, and that's defined as the number of homomorphisms from f into Gn, and then we divide by the maximal possible number of such homomorphisms that we could potentially have. This can be reached if this is just a complete graph. In that case, we actually get n to the k. Now, what do I mean by homomorphism? I mean a mapping of the vertices of f into the vertices of G. Typically, of course, n is large and k is small, so there will be n to the k such mappings, and they don't have to be injective at this point. And by homomorphism, I mean edge goes to edge, but we don't care about non-edges going to non-edges. So we're not looking at induced subgraphs or motifs, as they're sometimes called. We're looking at just homomorphism, so just subgraph counts. So by this normalization, this number here will end up between 0 and 1, and that's the reason why we call it the density. Now, this is sort of more sort of a combinatorial point of view, I'd say. And so for this theory, it's beneficial to switch to a more analytic point of view. And in order to do that, it's best to represent graphs instead of as combinatorial objects, we represent them as functions. And the way to do that is we're going to find a function kappa sub n that lives on the unit square and maps into 0, 1 interval and constructed as follows. So you start with your graph here, you write down the adjacency matrix. 1 means edge, 0 means non-edge, and you can see obviously it's symmetric because we're looking at undirected graphs. And then you just write this down as a function where black here stands for 1 and white stands for 0. And just to be clear here, this is 1 over n, and this whole thing here is just a 0, 1 interval. So that's the sort of way we embed this adjacency matrix into represented as such a function. Of course, you have to switch this to turn into the usual coordinate system. So here's our function that sort of represents the adjacency matrix. There are of course subtleties about this, but that's not that shall not be bothering us for this talk. Now it'll be beneficial or necessary to not just allow values 0 and 1 here, but allow any value between 0 and 1, any real numbers between 0 and 1. And so any such function will be called a graphon. So a graphon is just a symmetric function from the unit interval into 0, 1 into the 0, 1 interval. Now, what we need to do first is sort of re-express our subgraph density T sub fgn, which we have defined in terms of homomorphisms, and in terms of this, we want to represent it with using this graphon induced by this graph gn, and the way to do that is we write it down as an integral over these products. Now, what does this product do? It's just going through all the edges. So this just means I is connected to F, I is connected to J in this graph F, and then we pick the corresponding coordinates, and then we go through all through the whole space 0, 1. I mean, if you think about this 0, 1 here, this represents this interval 0, 1, and by integrating across 0, 1 here, at least one coordinate is just going through all sort of vertices of the graph, and then we do that multiple times, k times here, then you get sort of if you think about this, it's sort of a sum over all combinations of vertices, and this product here is just 1 if all of the edges are present in that particular part of the graph G head. So that'll be 1, otherwise it'll be 0. Okay, so now the beauty of this is that we're not restricted that this kappa takes values 0 and 1. We can just plug in any function here. So any general graphon, we can plug it into this formula and get a value. And so that's the definition of the subgraph density for graphons, is just this. So you give me a graphon, a function from unit squared to 0, 1. And I can calculate this subgraph density, which is just an analytic sort of object now, rather than a combinatorial object. All right, and so what's the cornerstone theorem of this dense graph limit theorem? That's what Lovas and Szegedi in 2006 proved. If I give you a dense graph sequence, now there's no randomness here at this point. It's just, this is deterministic. It's a sequence in this space of graphs, or you can embed it into the space of these sort of functions. If I give you such a sequence, and the sequence is such that for every f, these subgraph densities converge to a number that of course depends on f, then there exists a graphon such that the limits can be expressed as subgraph densities with respect to this graphon. So that sort of shows that this is a sort of complete metric space, or it is even compact in this case. So that's a rather nice way of expressing graph limits. And so we can think of kappa being the limit of this dense graph sequence. Now let's have a specific example that has randomness in it. Now, of course, the graphs are random, and so the corresponding graphon that you get is random as well, and the subgraph densities from that graph here, those objects will be random, right? Because we have underlying randomness. So let's assume we have a graph Gn that is an Erigeni random graph. That means n vertices, and all the edges are independent, present with probability p and not present with probability 1 minus p. Then number 1, that'll give you almost surely a dense graph sequence. So now, again, we are in a probability space, so we have to, these convergence now turn into almost sure convergence, and almost surely these random quantities now converge to these quantities over here, which are now deterministic. We can think of this Erigeni random graph to converge to a graphon that is just constant p, right? So how can we see that? Well, if kappa is just p, let's quickly go back and look at this expression here. Of course, if this is p, no matter what xi and xj are, then of course what I get here is the product, a p-fold product, a product of p as many times as we have edges in f, and so that's p to the number of edges. And then of course this integral is just 1 because it's the unit, the k-dimensional unit cube. Okay, now the main point here is that, as you can see, the limit is deterministic, right? So this is a sort of a first order approximation theory. And if you will, it's sort of the law of large numbers, or equivalent to the law of large numbers for sums of random variables. It gives you the first order behavior of these graphs. There's no, all the randomness of the edges has sort of disappeared, and we end up with this quantity on there. I mean, this graph one is just deterministic. You can generalize this to what one would call inhomogeneous Addition random graph, or a version of that. This is sort of the workhorse of dense graph limit theorem, and it's constructed as follows. So I give you a general graph on kappa, and the way you generate a finite graph from that is you sample sort of the vertex labels, u1 up to un. So you have n vertices, so each of them has a label, and these labels are IID uniform on 0, 1 on this interval. And then you connect I and j, vertices I and j, with property kappa ui uj. That's sort of sampling from this kappa in this randomized manner. And what the theorem is that, again, almost surely this is a dense graph sequence if this kappa is fixed, and almost surely Gn converges to kappa. In other words, if I want to write it down, Tf of Gn converges almost surely to T sub f of the kappa we started with. So we're not getting a different kappa, we're getting the same kappa back. And you can show this, I mean, actually pretty easily using like concentration results like McDermott's inequality and things like that. So that's sort of actually quite straightforward from using probabilistic off-the-shelf tools. So what's the problem statement? Now, of course, the natural question as probabilist is, well, what is the central limit theorem for dense graph limit theorem? In other words, is there a theory with which we can describe or sort of understand the fluctuations of random graphs? And I mean, as I said before, these objects here are random. So there's randomness in there, not just in the graphs, but we're just looking at these subgraph densities, there's randomness there as well. So is there a theory that sort of captures that? And two things I would expect from such a theory, I've written them down here. Number one, since subgraph densities characterize this convergence, all these, in the dense regime, everything can be expressed in terms of these subgraph densities. So they capture everything that needs to be known about these limits. Since that's the case, I expect that this theory also explains all these fluctuations of these subgraph densities. And moreover, there should be sort of a limiting Gaussian object, ideally, in analogy to the classical central limit theorem. In that case, I mean, there's not just a normal distribution that we get there. We have Donska's theorem that tells us that the partial sums converge to a Brownian motion. Or if you want to switch the point of view, you can embed your IID random variables in the central limit theorem. You can embed them into the 0-1 interval and sort of get a sort of a white noise process on the unit interval. And then if you integrate that, you get the Brownian motion. That's sort of the limiting Gaussian object that we have. So I would expect these two properties to come out of such a theory. So let's start in one place and see what we can do with sort of barehandedly. And so let's start again with this graph here. I give you a kappa. Now we fix kappa to be constant first. So that's the Addition random case, but later we'll look at the general case. So let's think of this workhorse model of dense graph limit theory and focus on the case where kappa is fixed p, Addition random graph. Now, for any connected f, we can show that the correlation between the subgraph density of f in Gn, and that of the edge density. So that's sort of the simplest subgraph density is just the edge density. And if you think about this, what this is just the total number of edges divided by n squared. That's what this is. So this is just capturing the number of edges in your graph and nothing else. And if you calculate the correlation between the two, you find that that converges to 1. It's a bit more complicated if f is composed of disconnected components, but in essence, the story is the same. The fluctuations, the dominating fluctuations of this object here is determined, or in essence, the same as the fluctuations of the total number of edges in your graph. And well, this object we understand well because, for example, in this constant case, well, that's just a binomial distribution divided by n squared. So we know everything there is to know about this object. And if you scale it appropriately, we get a Gaussian limit. So that's that. And is there sort of a Gaussian limit point of view? And the answer is yes, in this following way. So we could give me a second. My daughter is. Okay, sorry. So the answer is we can do that by considering the following measure. So you take your kappa n, which is the one given by the graph Gn, and you sort of subtract the expectation, which in this case is p. So this gives you sort of a signed graphon. And if you scale it properly, you can interpret this as sort of a measure on a space, what I call D2. So let me quickly draw the picture. That's just this half quadrant here. So that's just D2 over here. And so we can think of this as a measure on this assigned sort of, or the density of a signed measure here. And we can show that this converges to what's called a Gaussian stochastic measure, or loosely speaking, a white noise that we can call Z2 here on this space D2. And so this sort of measure converges to this white noise. Now, the way to show this mathematically, since I put white noise in quotation marks because the term white noise has a very specific meaning, for example, in Hida calculus, where it's sort of a generalized function. So I want to avoid that and use the appropriate term Gaussian stochastic measure to show, in order to show this, what we need to show is, well, of course, we integrate a test function against this measure and show that that converges to the integral when we integrate the same test function against this white noise. And so the right-hand side here has a normal distribution. And so that's the sort of result that we get. I mean, this specific result here is just, if you plug in phi equals 1, then this is just the sum of the edges, and that's just converging to that the integral across the whole white noise sort of field. So that's the case for kappa is constant. And what about the general case? Well, it's sort of something peculiar happens, namely the subgraph densities now are dominated not by the edge counts, but by functions of this form. So they are dominated now by a sum of independent random variables, which are sort of transformations of the vertex labels. Okay, where the function g here depends on kappa and f, but ultimately they are dominated by just the sum of ID random variables. In other words, the fluctuations of subgraph counts is dominated by vertex labels, and in this case, all information about the randomness in edges is completely lost in the limit. At least in this case, we still had some information about it, in the sense that we get this field, this white noise field on Z2, so the sort of the white noise field on D2. That sort of expresses the edge randomness, but here we completely lose it, and the dominating effect is just the labels, which is not very interesting in that sense, because we're not really interested in the labels, we're interested in the edges. So of course you can start to sort of do ad hoc things, like sort of trying to subtract the kappa that is sort of depends on the U, or things like that. I mean, you can do ad hoc things, but what we're looking for is sort of a coherent theory that captures more than just sort of this part. So that's not what we're going to do. As I said, this sort of first approach gives us some insight, but is not satisfying, because all we're looking at really is, in the constant case, edge counts, and in the general graphon case, vertex labels, which is just not useful for statistics. We're not interested in the vertex labels. These labels are sort of artificial, so we're not interested in those. And so it turns out that the right way to look at this, we believe, is through the lens of generalized U statistics that was introduced by Janson and Nowitzki in '91 in the context of random graphs. So let me quickly tell you what a generalized U statistic is. So it's essentially a U statistic. You can see here, that's the U statistic part. So you have IID random variables UI, and we're summing over ordered indices, or ordered tuples of indices. And so you will recognize that as a U statistic, but a generalized U statistic on top of that can also depend on more random variables, in the sense that we can add here a random variable for each pair of these indices, where the Vij are just also IID, but can have a different distribution than Ui. So that's these are generalized U statistics. Now it turns out that these generalized U statistics are much richer, not only than sums of ID random variables, but they're also richer than U statistics, in the sense that there are fluctuations that are sort of orthogonal to the dominating fluctuations. There are fluctuations of smaller order that are orthogonal and important as well to describe this whole object. And so what we're doing is essentially applying sort of this theory to the dense graph limit theory, and we sort of generalize it in some aspects that I will talk about later, and we'll complement this with rates of convergence using Stein's method. So let me give you an executive summary of the results, sort of the high level picture. It turns out that these subgraph, I've spoken about the dominating fluctuations of these subgraph densities. It turns out that you can actually look at not just the dominating fluctuations, but you can look at fluctuations of any order, because they're smaller order fluctuations with a smaller variance, and they're orthogonal to them, they're orthogonal to each other. And these fluctuations are all, in essence, and there's a specific meaning to in essence determined that I will talk about in a second. But they are in essence determined by statistics of this form. Now it's a long formula, so let me guide you through it. First of all, this is a generalized U statistics itself, in the sense that we are summing over these ordered tuples of indices. So this here is just formalizing this space of ordered indices. So there are n choose k elements in here, and the nice thing about this sum is, first of all, the summands themselves are uncorrelated. So we already can tell immediately what the correct scaling should be. It's just n choose 1 over square root of n choose k. That's the correct scaling, because it turns out that these summands are uncorrelated. Now let's start from the back here. You can see that now, instead of looking at subgraph counts, if you will, we're looking at centered subgraph counts. That means we're taking these edge indicators. So these are the edge indicators that are 1 if there's an edge between AI and AJ, and 0 otherwise. And so what we need to look at is instead centered subgraph counts, where the centering is not the overall expectation of that, but the expectation given UI, given the conditional expectation given the vertex labels. So that's the sort of thing that we have to look at. And you can see that's where the generalized U statistics comes into play, because this is a function of these additional random variables that we allow here. In front of here, we need to allow for a certain for general functions of the vertex labels, and we've added here sort of a test function, or a weight function, that will help us sort of describe the white noise, the white noise field that we're getting. So this is just sort of, as we did before, we integrate against a test function. That'll be this sort of weight function. So again, these statistics determine, in essence, the subgraph densities, all of them, jointly. By in essence, I mean, you can approximate, so you have these different orders of variances in your subgraph densities, and you can approximate any of these to any degree of precision that you like, with products of these statistics and linear combinations of these statistics. That's what I mean by in essence determined. But once you know these statistics, you can essentially reconstruct to any precision all of these subgraph densities. As I said, the summands here are uncorrelated, which is nice, because means they're easy to scale, because you know the scaling immediately. But moreover, they are also uncorrelated across different f's. So if I give you 2 different f's, then they are going to be uncorrelated. What's important here, I forgot to mention, that's the most important part. We only need to do that for F connected, okay? So if, yes, so we only need to do that for F connected, essentially. So since we're looking at these ordered tuples here, even if F and F prime are isomorphic, even then they are uncorrelated, because, well, how do we see this here? Well, you can see it over here. The reason that we are normalized or centering by the conditional expectation. What's the conditional expectation of this given U? Well, it's 0, because that's the conditional expectation of that given U. So if you take now products, as soon as only one of these edges appears alone in any of these products, the conditional expectation is 0. That means the overall expectation is 0 as well. So in order for any of these terms here when you take the product here and take expectation, in order for any of these products to be non-zero, you need a perfect overlap of all these edges, which you can't do if these are different, because we're looking at ordered sets. Okay, and especially if one has more edges than the other, there's even more so. There's not possible to get a product where every edge appears at least twice, and so that's why we have a lot of orthogonality here. Now, what are the Gaussian limits? So that's sort of I think that's sort of the most interesting part of this project, is sort of identify what the limits are. Let me here focus first on the easier case, which does not quite fall into this Janson Nowitzki generalized U statistic theory, because in this case the UI are not independent, but we can put them on a sort of lattice of span 1 over n, and so we just put UI equals I over n. They're independent, non-random, and particularly independent, but they're not IID, and so that's sort of a case that is outside the general theory, but it's something we can still handle. Okay, so let's assume that, so that we don't have this vertex, so this randomness from the vertex label sort of doesn't disturb here, so we get a cleaner picture. We fix an F, a connected graph on K vertices. Again, dk is this half orthant, K-dimensional orthant here, and then we can show that this test statistic, or let's call it a test statistic, converges to a integral against a white noise or Gaussian stochastic measure on the space dk. Okay, I put a 1 here because that's just because this is not random. It's sort of, you can combine it with this. So it's really, if these are deterministic, you can sort of combine it with that. So that's why it's not really, in this case, this is not important. But the test function is that, so the weight function is still there. Okay, so this converges to a normal distribution, and we can express these limits, these Gaussian limits, in terms of an integral over a white noise measure. And you can see the white noise measure lives on the sort of K-dimensional half orthant, and it has an infinite, well, this is so-called infinite decimal variance of the white noise. That means at the point T, there is that sort of Gaussian point has a variance that is given by this product, and you can recognize it. That's just the conditional variance, or just the variance of this product here, and given these values. That's just that. And you can see the measure here is not homogeneous over dk, and there's no reason why it should be homogeneous, because the vertex labels are not, this is not a vertex exchangeable graph, and so the vertices are not IID, so therefore we're not expecting a homogeneous white noise field, in the sense that these infinite decimal variances change across the field. Now, what's the picture in the more general case when the UIs are IID? So that's, again, that's the sort of the workhorse model of dense graph limit theorem. We can show now this psi function here is important because it sort of captures the randomness in these vertex labels. But again, it converges to these things converge to a normal distribution, and we can express it in terms of integrals against the white noise measure, where now we have to augment this space here. So this is sort of capturing the randomness on here, sort of captures the presence or absence of these centered subgraphs, and this sort of captures the randomness in the vertex label, so we have to augment that. Now, what's interesting here to point out that this measure, this white noise is homogeneous in this dk. Okay, so if you look at the infinitesimal variance of the white noise at TU, you can see that it is homogeneous in T. Okay, and that's what it ought to be because of vertex exchangeability. These things are vertex exchangeable, and so we expect it hope to be homogeneous. If you want to get rid of this vertex label variance on sort of set psi equals 1, you sort of integrate that part out. You can see that you get a homogeneous white noise on dk with infinitesimal variance to be the integral of this object. Okay, so the integral of this against du, which is then just a constant, which is homogeneous across the whole sort of field dk. So that's sort of, I mean, there's in dense graph limit theorem, there's the issue of that the limiting graph funds are not unique because they're only unique up to measure preserving transformations, and sort of this is reflected here by the fact that the fields are homogeneous, which means that you can apply any measure preserving transformation to this field here and you get the same in distribution. So it is invariant in that sense. Okay, so this result holds jointly for any finite collection of connected F, and moreover, these white noise fields ZF are mutually independent. And so if you want to think of the limit, the limiting object is the family of these white noise fields indexed by script F, which is the collection of all finite and connected graphs. If you want to talk a little bit more detail about our main result, I mean, what is it we actually prove beyond what Janson has done in his work in the 90s. So given kappa graphon and given a sequence of connected graphs, those are the graphs you're interested in. And each of these Fi can live on a different vertex set here, or they can be the same, they can be isomorphic, doesn't matter. And again, these DKs are these half orthons. And then for each F, you can give a different function phi I. This is sort of the weight function, and the psi I is sort of a function of these vertex labels. And all we need here is that the UIs are independent and taking values in 0, 1. Of course, this 0, 1 space here is sort of arbitrary, can be any Polish space, but you can, without loss of generality, we can assume it's 0, 1. They don't only have to be independent, they don't have to be IID. And the Yij, what we have typically is that there are Bernoulli random variables with this conditional on U having this sort of mean or success probability, but we can generalize we can be more general in the sense that all we need is that the expectation of that given U equals to kappa Uij. But I'm sticking here to the sort of graph world where Yij is 0, 1. So what's the main statistic that we're looking at? We're proving a multivariate normal approximation theorem, and here's our main statistic. So these are these centered subgraphs, called centered weighted subgraph statistics. If these Fi are big, have 2 or more vertices, and in the one vertex case, well, let me quickly go back to this here. Where was it? If F is just consisting of one vertex, of course this part disappears. That's just set to 1, and we only have this part. So in that case, of course, we have to sort of center this thing manually. Otherwise, these things already have expectation 0. In this case, we have to sort of center manually. And sort of, as you can see, this sort of captures the sort of the U statistic effect, which is the dominating effect from the U statistic. It's just a sum of the so it's just functions of these vertex labels. So we put them together into a vector, and that's the object that we want to analyze. And surprisingly, when we tried that, none of the existing theorems, at least using Stein's method, works in our situation. And the reason is that these things are dependent. I mean, there's dependence within these sums, not in this case. This is just a sum of ID random variables. We've only included it because we need a joint convergence of this and a collection of these. We need joint distribution. Individually, of course, this one is just a central limit theorem, but jointly, of course, there's work to be done. And so these sums here are sums of dependent random variables, but they're uncorrelated. And so that's the sort of situation that has not caught much attention in the literature. So all these like standard results on local dependence, they sort of do not really work in the uncorrelated case, where the variance is much smaller. It's usually you divide by the variance, and if the dependence is still there, but you divide now by a smaller variance, you're just not getting any convergence out of it. So we sort of had to sort of develop our own Stein approximation theorem to work in this case. We can write down the covariance structure of W pretty explicitly, because they're sums of uncorrelated random variables. And so if Fi and Fj are not equal, then that covariance is just 0. If Fi and Fj are just one single vertex, then you can just write it out. I mean, that's just 2 lines of calculating that, and that's the same for if Fi and Fj are the same. So I mean, you could just get these expressions. They're only diagonal terms when you calculate the variance. There are no covariances because they're all 0. You can see a little bit here. It's a bit more complicated because we don't assume that they're IID. So we have to sort of, every single U appears in here because they may not be IID. But you can sort of see the answer. You'll get an underlying Hilbert space structure from this. So if you replace this by sort of an integral here, then you get sort of an inner product, and that will gives us the limit, the structure of the limiting white noise field. And here's a sort of the main theorem. If Z is a d-dimensional Gaussian vector with 0 mean and the same covariance structure as W, then we can bound what's called the convex set distance between the 2 vectors by constant over n to the 1 over p plus 2, and where c is of course independent of n, but can depend on all the other things. And p here in particular is the maximal size of the subgraphs that you're interested in. Now, what we actually do is sort of we prove such a theorem for smooth test functions, in which case we get an optimal rate of 1 over square root of what we believe to be optimal of 1 over square root of n, but they have to be really smooth. They have to be p plus 2 times differentiable. And when you're interested in this sort of non-smooth metric, you have to sort of interpolate, and that's why we lose a lot of rates here. But I mean, there's no reason to assume that this is optimal, but who knows? Okay, so what's underlying this is a sort of an abstract approximation theorem. I don't want to go too much in. This is too much into detail. This is the version d equals 1, and the fact that these things are uncorrelated, the summands are uncorrelated, and therefore the variance is much smaller, makes life very difficult. In particular, those who know those Stein theorems for exchangeable pairs, there's usually 2 terms. One is this variance of the conditional expectation of GD in terms of Stein couplings, and then we usually have an expectation of GD squared, and that's usually the easy term. But in this case, because they're uncorrelated, this absolute value inside sort of destroys a lot of the structure. You cannot exploit the fact that these things are uncorrelated. So this is the problematic one. For the reason that I don't fully understand, by cranking up the moments here high enough, this term becomes small enough so that we get this convergent like 1 over square root of n, at the cost of having like sort of intermediate terms. So this is sort of the usual exchangeable pair theorem, but sort of on steroids, because we have now not just variance of conditional expectation GD, but we have to do that for all powers of d up to the degree that we need here. And of course, this is the univariate version. The multivariate version is you have to do that for all mixed moments. And so that's what we end up with, is essentially having to bound moments of these subgraph count statistics. Oh, sorry, centered subgraph count statistics. So let's have a quick discussion. As I said, the limiting object is sort of this collection of white noise processes living on these spaces here in the lattice case, and in the uniform vertex label case, we have to commend it by this thing here. So that's that. So we sort of identified the limiting objects. Of course, now you can start to think about putting these white noise processes either think of them as generalized functions and do that in sort of heater calculus world, but which is sort of quite difficult to do. And or you can start to sort of integrate the white noise and extract some Brownian sheets out of it. And that's sort of future work. I'm not sure how fruitful it is because of the ordering of the vertices is still arbitrary. So if you start to integrate these white noises, you have to decide on an order, and that's usually not the order is sort of arbitrary. So I don't know how much meaning we can attribute, give to these Brownian sheets. So I'm not sure how fruitful that would be. But let's go and talk about statistical applications, because that's sort of I hope that this theory sort of opens up a new world in how we can test or do statistical testing for random graphs. But first it's important to mention, I think, that this workhorse model, where the U's are IID, the vertex labels are IID uniform, is problematic because it conflates the randomness of the vertex label with the edges. Usually we're only interested in the edges. We're not interested in these vertex labels. So that's sort of, this model has too much randomness in it. It's just a sort of a mathematical convenient construct, but for statistical purposes, ultimately, it is not very useful. So it's probably best to think of the data conditionally on the vertex labels. And I think that's sort of essentially the lattice model, where you say, okay, UI is just I divided by N. Essentially, you order them in one way or another, whatever is convenient. What's important here is that if you want to evaluate these centered subgraph statistics, you need these values, right? So you need an a priori hypothesis. Of course, you don't need the UI and the UJ. What you need is this centering value, the conditional, or what's your hypothesis, given the vertices, what's your hypothesized connection probability between any two vertices? That's what you sort of need. And okay, so ultimately that's what our test statistics look like. Of course, now the weight function here, we can just set it to 1 because we're actually interested in an overall test across the whole network. There is no reason a priori why you should have weighted sums. So we just put everything in front here equals to 1. So we have these ordered sums, we have this normal, this scaling, and we have these centered subgraph counts as subgraph statistics, and where the Pij here are just the hypothesized edge probabilities between vertex I and vertex j. So you need to have that in order to evaluate this. And then, of course, the choice that you make about which subgraphs you're looking at sort of determines what the overall test is sensitive to, right? That's sort of a choice that the statistician has. So let's look at a few examples. Again, the easiest one is just where you pick F to be an edge on two vertices, and that's just testing the total number of edges against the expected number of edges. That's just essentially a binomial test if you want to think about it that way. So that's sort of the not very interesting because you're not making any use of the graph structure. So in order to get the graph structure into play, the next thing you can look at are what's called 2 stars, and there are three of them because we're looking at ordered statistics. That means we have to go through all of them, but they're all uncorrelated. We can just add them up and divide by square root of 3, and so that's normalizing it. It's sort of convenient. You just add them up. What does this test do? Well, it sort of tests for pairwise dependence. How do you get a large positive value for this? Well, let's quickly go back. A large positive or a positive value you get if both, if you look at 3 specific vertices where either both edges there are present or both are absent. If they both are absent, we have 0 here 2 times, and you get minus times minus is plus. So that's the way to get a large value. Either so we have an increased simultaneous presence or absence of adjacent edges. Okay, it could also mean a systematic over or under specification of our connection probabilities. That could also be the case, I think. By that I mean that if in some part of the graph you have an over specification of the probabilities, and in another part you have an under specification. If there's just somewhere the probabilities are too large than what they should be, then you sort of this test would sort of catch that. But if in one part is over and in another part is under specified, then sort of this sort of statistic will catch that as well. And what would large negative values give you? Well, sort of give you sort of that would mean there's a repelling effect. If there's an edge somewhere that sort of suppresses adjacent potential edges. You can play the same game with sort of triangles and see that what does it mean? A large positive value means there's a lot of simultaneous presence of triangles, or 1 on and 2 off configurations, things like that. So just to clarify, I mean, if you brought it now to this level, we have to realize that what we're actually doing is just testing independence of a sequence of coin tosses. I mean, that's ultimately what we're doing, because if I go back, I mean, the graph structure comes only into play by the way we sort of set up the statistic, but these were, because now we're looking at it conditionally on the vertex labels, because that's what I think what we should do, then these are just independent coin tosses with the corresponding probabilities, and they don't have to be the same success probabilities, but they're being modeled by what we think are the connection probabilities. And so the different subgraphs essentially detect different types, or sensitive to different types of dependence in your sequence of coin tosses, of course, geared towards network applications. There's some sensitivity towards motives. I mean, just like here, there's sort of motives that we're detecting, like here, 3 edges are on and 1 off, 1 on, 2 off, that sort of motives or induced subgraphs. But you cannot say, okay, why don't we just look at motives themselves individually? You're running the same problem. Testing individual motives, it's the same problem in the sense that motive counts are dominated by smaller subgraph statistics, and you're just turning in circles, and you end up again having to analyze ultimately these centered subgraph statistics. So yes, you're looking at motives, but you're looking at sort of a weighted sum of motives, and the weightage is done in the right way so that these different statistics become uncorrelated. Typically, you don't have these probabilities given to you, but if you sort of fit a stochastic block model where you assign different vertices to different communities, and then you estimate within community and across community probabilities, that'll give you estimates for these Pij. Of course, if you want to do testing, then you have to adjust the p-values because you have already used the data for fitting, and so you have to be careful. But it's sort of, you can use these statistics as sort of a sanity check whether there's any dependence left after you fitted the model that's sort of standing out that you should be aware of. And of course, now that we have that, we can start to ask questions about what's the sparse case, and so I don't really have any thought too much about it, but I gather that the situation might be a little bit more complicated. All right, so I think I will leave it at that. 45 minutes are over, and so I want to thank you at this point. The paper here is where we discuss all of that is this paper called Higher Order Fluctuations in Dense Graph Random Graph Models. It's the same title, and much of the sort of the theoretical sort of abstract theory is coming from these papers, and in particular this book Gaussian Hilbert Spaces. And there's one chapter on generalized Q statistics, and there's a lot of abstract material in there that we have to sort of adapt to our situation. Okay, thank you very much. That's it.
Thank you. On behalf of the whole audience, my applause coming. Thank you very much, Adrian.
Thank you.
Thank you. Okay, so now we have got several minutes for questions, answers. So please, maybe because the audience is relatively small, so just ask questions and see how it goes.
So, Adrian, can I ask a question?
Yes.
You hear me? Yes, that's good.
I do. I do.
Excellent. This GNP thing with the subgraph counts being essentially correlated strongly with the total number of edges.
Yes.
Is there any theory, useful theory, sort of one level down, if you condition on the number of edges and sort of do GNN? Or does it just destroy all the independence that you need to make things work?
So you're asking about sort of answer the GNM model, right? The original Adrian Röllin model, where you fix the number of edges and then you look at that. I haven't thought about it. I suspect you will end up with these. Well, yes, I haven't thought about it, but I mean, I suspect you will end up with these 2-star statistics. That will be the next level of fluctuation. Will be these 2 stars, and then you sort of have to. If you adjust by the number of edges, then if you center it, you essentially remove the expected number of edges and sort of you ought to be morally ending up with the same sort of statistics as we do now, because what you can do is sort of, you can condition on the edge density, and then at least asymptotically all the other centered subgraph statistics are unaffected by this conditioning, because in the limit they're independent. So you would expect that in a finite n case they are close to unaffected by this conditioning, and so these smaller order effects will be the same in this GNM model.
Right.
They would look similar as to what we have in the GNP model.
Okay, thank you.
That's conjectural. I haven't thought about it.
Okay, so maybe some other questions, please.
Adrian, have you thought about the sparse case, the graph X's, and it seems like it's pretty similar, right?
Yeah. So I had this slide, and I think so the multivariate normal approximation theorem should go through in the sparse case as well. Not in the very sparse case where the degrees remain bounded, or the expected degrees remain bounded, but where you still have this intermediate regime where the degrees grow, but not as fast as n, not linearly. The multivariate normal approximation remains. So sort of the fields, these white noise fields that we have now, they will still be there, but there may be additional fields that you have to sort of add to it to sort of capture additional randomness. For example, the graphics model has a random number of vertices in it. So if you construct the graphics, a graphics random graph, the number of vertices is random. So you have to sort of take that randomness will also come into your white noise fields. And so I sort of conjecture that's what's going to happen. Our theorem still will work more or less. It's just that whether the fluctuations of the subgraph counts can be decomposed in exactly the same way so that everything is captured by the subgraph statistics that we have now, that I don't know. Some of it will be captured by what we have, but whether it's all of it, I don't know. For the dense graph case, everything is captured by the centered subgraph statistics. In the sparse case, that may not be the case.
Yeah, I mean, it looks like this multivariate normal theorem you have, it's quite general, right? As long as you have some model where the edges are independent. Or
yes. That I have no doubt that goes through. If you work a bit harder, because now the p sort of the probabilities go to zero, so you have to work maybe a bit harder, but it should be going through morally. But again, whether the high level story is the same, I don't know.